Record. All right. In the ta-da nick of time. It's 2:20. How about that? We don't have Zach yet. And he's not on Zoom either. Except for somebody just beat that. And that was Josh. Okay. So only one more assignment left to do, and that is Project 5. It's due Thursday, April 22nd. I want you to read about these three imagers that we're going to talk about today and make some engineering judgments on what you think they're good for, is the whole idea. Okay. And the final exam is optional. Hopefully we'll have some more. I will get to your Project 4s maybe tomorrow. It's been a busy week already, but finals are written. In theory, I have nothing left to do until finals start, except for grade and do lab stuff. Okay. But I think everything's calmed down.
I need to be a full-time lab person.
And I can go back to being a full-time. I go back to only having one job.
And getting paid for 2.
And getting paid, no, getting paid for 3. Okay, see, the thing is, my year-round 9-month check. Okay, I'm on a 9-month contract, and NAU literally pays me like I work 9 months out of the year. It's not like a full-time salary. But that's spread out over 12 months. So I get, but all my health care and all my benefits and everything are taken out of that 9-month salary. And then in the summer, I get a check that is about, is it twice as big? No, it's probably about 1 2/3 of my other check. So I get my regular check plus I get 1 2/3 of my check because there's no benefits taken out of it. So all my summer salary pretty much just goes into savings. I live off of the 9-month salary and I'm good. I don't have any debt. I can do that. One of the wisest things you can do in life is don't accumulate debt. It's tempting, but it's not worth it.
Oh, so very tempting.
It's oh so very tempting. Just don't do it. The final exam, if you choose to take it, is Thursday, April 29th from 12:30 to 2:30. They will be graded by 3. It's open book, open notes. You can either come into Zoom or you can come into the classroom and take the exam. Either way, it's at the same time. I'm not rescheduling anything during finals week because it always gets me into trouble. We're going to talk about imagers. This is what I did as an engineer. Dr. Brower talked about one imager in particular. I added a couple to it, and this is the idea behind Project 5, which doesn't involve mentor graphics. It's a good way to boost your project average, is to do Project 5. We're going to read about these 3 imagers and figure out, they all have different benefits to them. They all have different applications. And they all have different specifications, and we'll talk about some of those specs today. Time to leave, go home, and give everybody extra credit. So this is a review. The idea is what we want to do with these imagers is convert photons to electrical signals. So every photon that comes in, where's my little do thingy? Every photon that should come in would ideally produce 1 electron hole pair. But not every photon that comes in does. So this leads to the idea of quantum efficiency. And quantum efficiency is just telling you what percentage of the electron, what percentage of the photons actually produce electrons. But to get an electron out, we need the energy of the photon bigger than the band gap energy. And the energy of the photon is Planck's constant times the frequency. This is a physicist talking, so they use V for frequency. What?
It's very upsetting.
And since C equals lambda F, we know that we can convert that into wavelength and call that HC over lambda. Turns out for silicon with a band gap of about 1.1 electron volts, it will convert things that have a wavelength shorter than about 1 micrometer. And this 1 micrometer is down in the near IR. Anything with frequencies higher than that are things like light and UV radiation and those horrible cosmic photon events that the guy from Johns Hopkins would study. Yeah, we built a sensor for those ones too. So the idea was what Me Too, and I'll give Me Too credit first because I like him. What Me Too and Sabrina, because I like her too, and the other guy came up with. He was okay. He was just he's a little arrogant. Let me put it that way. I had to put up with $500,000 of useless test equipment because of him. And and the reason why I bought it is because I thought the sales girl was cute. It was $500,000 I could have spent on something useful. Okay.
$500,000 of making the sales girls.
Yes, or that's a story I was told. I wasn't actually there. That's what they blamed it on. We have a photodiode. We're burying it on the substrate. So the P side is already tied into our P substrate connection to ground. The N plus side is the only side I really control. I'm going to have to put some voltage through a switch, which will be something like a MOSFET, and put voltage on this N plus region. If I put positive voltage on it, I'm going to reverse bias it, create this depletion region, and if a photon hits the depletion region, it will generate an electron hole pair, which will make the depletion region smaller. So my voltage is going to read down. It's going to go from a high reset voltage down to 0 if I completely saturate that pixel. That's what that slide says. Now, if I look at the pixel itself, I'm going to need a couple of transistors, 3 to 4, depending upon whether you're an IR person or a visible light person. So, or even more transistors. Some of the active region of this pixel is going to be other transistors, and only a small portion of it is going to be actual pixel. So this leads to a specification that you'll be reading about for Project 5 called fill factor. And fill factor is literally the percentage of the pixel that's diode. Now, astronomers were really upset over something like this. They didn't want any of the pixel to be readout electronics. They wanted the entire pixel to be light collecting area. So they wanted as few transistors and as small transistors as they could get in there, and as big of pixels as they could also get in there. Something like this is more of a commercial imager. I have light, I have various shades. So this might be red, this might be green, and this might be blue. Filters on here. And so for this pixel here, I got labeled R, only red light would pass through this filter. And the red light would get focused by this little micro lens onto the area that's actually the active area. And the rest of it, I put a blocker on top of it, because if light comes through here and into this region, it could produce electron hole pairs that would basically just be noise and would disturb the rest of the system. So that those little light blockers, these little light shield, I'm going to put over the area that is not active region. That would also upset the astronomers enormously. Most everything upsets them.
They're very fragile.
They're very fragile. They want all their electrons, and they don't want any noise, and that's why we call them the nommers. It's our special name for them in the lab. Right, okay, we talked about all those things. I could speak Nommer though. I can still speak Nommer. It's scary, and its close cousin, which is, believe it or not, this is an actual job title, astrogeologer. Astrogeologists,
Astrogeologist, not
geologists, sorry, astrogeologists. And there's a whole bunch of astrogeologists sitting up at the top of the hill in Flagstaff.
over at Lowell.
No, the astrogeologists are mostly over in the physics department and at USGS. This is the world headquarters of USGS astrogeology. Scary, some of the languages I can speak. So what we've got here, we've got this photodiode. When a photon comes in, and photons are usually drawn like this, they're drawn as squiggly lines. When a photon comes in, it gets into the depletion region, it gets absorbed and creates an electron hole pair that's going to draw, oh, this is a photovoltaic cell, so we're doing this backwards. So what this is going to do for a photovoltaic, this is like a solar cell on your rooftop. You got a solar cell on your rooftop, photons come in, they generate an electron hole pair. You rig this thing up so the electrons go this way, the holes go this way. We have an electrical current now flowing in this direction. So you can use light to produce electricity from the same effect. It's called the photoelectric effect. It's amazing, and I thought everybody knew about it. And this was the history as I saw it, because I was mostly working in astronomy at the time, or working with people who were developing technology for astronomers, or navigation cameras or stuff like that. In our little, what do you want to call it? Our little piece of the universe, our little guild, the guild of whatchamacallit, of astronomical imaging engineers. The guy who founded it all was Jim Janicek, and he was at JPL, and he developed CCD technology for astronomers. There were other people in other fields, mainly black ops, people trying to look at missiles and look at pictures of tanks and things like that. Bob, yeah. It's not Bob Hoffman, though. This is Alan Hoffman, Jim Woolaway, and his group, Alan Hoffman's group at Hughes SBRC. It was really everything's a group effort. But they developed indium antimonide, and we call that INSBE, and platinum silicide, we call that platinum silicide, infrared detector arrays, and they were primarily for black ops. The advantage of the INSBE was it had really good quantum efficiency, really low noise. If you're looking at something that didn't have a lot of signal, it was great. They were like $100,000 a piece. And the platinum silicide were like $5,000 a piece, because you could build that integrated all into one chip. The INSBE diodes, you had to squash them together with the CMOS readout to get them together, and that was the big reason why they were expensive. Rockwell also developed their own technology. It was based on mercad telluride, and that's what we called that. They didn't have quite the quantum efficiency and had a little higher noise. There were astronomers like the Rickies, George and can't think of her name now. Ken Don works for the Rickies down at University of Arizona that liked these mercad telluride arrays, but their performance wasn't quite as good. But they swore that they were okay. Al Fowler, at the time he was at Kitt Peak on campus at U of A, it was the first non-military application of infrared arrays. And the real reason why SBRC was willing to just hand these $100,000 arrays underneath the table to Al Fowler was they wanted pretty pictures that they could show to the world of what these IR arrays could do. So we took pictures of stars, and they ended up on the SBRC promotional posters. And this is how IR astronomy gets started. A lot of things get started like that. And then promotional posters, yes. That's why they wanted, because they can't put pictures of tanks on their promotional posters, because then people know what they're looking at. Like, we don't know what they're looking at. They're looking at military stuff. They're looking at military bases. You can put, because some of that's classified, you can put pictures of stars and the Orion Nebula and comet crashes on Jupiter and all kinds of good stuff like that on your promotional posters.
And stock photos of people soldering.
Yes, and stock photos of people soldering things.
Soldering iron.
That would have upset the astronomers. So we made these pretty pictures for the promotional posters, and that was our job. That we never had enough money to actually have them build an array for us. So all the astronomical arrays were optimized for tanks. Then finally, the Naval Observatory, who has very deep pockets here in Flagstaff, funded us to actually build an IR array for astronomy. Now, once we got the IR readouts working, Eric Fossum, who was originally a memories engineer, and he got his degree, for his PhD from Yale, and he and then he went to Columbia University to teach, and he had a research group there. He took the idea behind the memories and the IR arrays and put those photodiodes directly in the substrate in silicon that could see in the visible light, and came up with the idea for the CMOS imager, which is basically the technology that allows us all to talk to each other. From Yale, he went to Columbia, and then he went to JPL, and then he spun off a company called Photobit, and Photobit got sold to Micron and became about 1/3 of Micron's business for about 10 years, was the imagers. So that's where my ties from Micron come from. And basically, they just merged all those technologies together and created the CMOS camera.
So you use cadmium, right?
Yeah, it's mercad telluride.
Okay, yeah.
Mercury. And that should be Hg, not Mg.
Yeah.
That's magnesium.
Yeah.
Okay.
Magnesium, cadmium.
It's mercad telluride. It is with an H, okay. No matter what I wrote there. Okay. So that first detector array that came about for IR astronomy was called Aladdin, and we put it in a lot of instruments that ended up on the Gemini telescopes and some of the telescopes on Kitt Peak. But the really expensive ones, and this is like this one right here, we called it Phoenix because it was the 3rd time someone attempted to build this spectrometer, and we did it. Yes, and that's why it has, it's Phoenix, and that's why it has the Trans Am Thunderbird on the front of it. So what we did here, this was our specification. We optimized, it was originally a 3 transistor cell is what they had in the readout cells, what they had in the thing for the black ops. We added a 4th transistor into the pixel that basically clamped our voltage, so we had a higher number of electrons after we did reset available to do conversions. So we could integrate a little bit longer. We could take, pictures that took an hour to take, and with a reasonable background level. So first thing when we're looking at for an imager is the number of pixels. And what we had then, this was a 256 by 256 array, and we built a 1024 by 1024 array. So our pixels, we had 256 by 256. So 65,536 elements. The pixels were 30 microns by 30 microns. And geometrically, 28 by 28 micrometers of that was actual photodiode. The other 2 micrometer strip, 2 micrometer by 2 micrometer strip, was the 3 transistors for the readout cell. So the fill factor geometrically came out to be 87%. That really upset the astronomers. So this is where me and this guy right here, George Simmons, made this little, it was great. It was 1920s technology. I loved it. We built a pinhole camera using tinfoil and a little needle. And we built a 10 micrometer spot pinhole camera doing this with some chewing gum probably involved too. And the idea was what we're going to do is scan across the pixels with this spot, and as we go across, do we see any dead zones? Do we see any place? If I add the total light between the two pixels, what do I get? And what we got beautifully, our light levels went like this. There was no dip in between there. So we declared it to have 100% effective fill factor. All the light that hit the array got to one pixel or another. We had a PMOS source of PMOS because it's lower noise than NMOS, a little slower too. Source follow, SFD stands for source follower per detector, meaning we had an amplifier on each cell, we had a readout on each cell, and those got multiplexed into 4 outputs. And these 4 outputs were also source followers, so the gate to these transistors was exposed to the outside world. And again, the astronomers will not let us use ESD protection, because protection diodes might mean that they lose a couple of electrons. So no ESD protection on this chip. We spent $1 million on it, and we got exactly 1 perfect array out of it. We got a lot of very good arrays.
Very good.
Yes, they got scattered around the universe to build instruments. No ESD protection. We had this ESD protection protocol that involved no one could handle the array unless 2 people were there. And one of them had to be me or Al Fowler. And then the other person had to be a technician trained by me and Al Fowler.
So Al's the one that went to the South Pole.
Al's the one who went to the South Pole. And Al usually wasn't there when we handled the array, so it was mostly me. And one of the guys we trained was a technician with a drinking problem, let's put it that way. He would go out for lunch and come back sauced, and no, you're not handling the arrays today. We covered for him for a long time. I don't know why. He ended up leaving and stealing a bunch of equipment. And then this guy right here, this guy right there. I don't know what I just did.
Did you say he was like the boss?
He was the boss. He comes out and says basically, "Oh, I'd hire Charlie again." I'm like, "Oh, no. Charlie's not in this picture either." Okay, so things we need to worry about here. Okay, so the IR detector, it's thin to INSB. Remember that thing we talked about was if I have a photodiode and I have a thick layer of material between there, some of the photons as they're coming in are going to get absorbed by that material and never make it to the depletion region. So actually what they did is they took a little sander and sanded them down so to thin that backside. So you got less absorption in between there. Wavelength range 0.9 to 5 microns. Remember, visible light is probably about 0.7 micrometers, 700 angstroms, or 700 nanometers, I should say. So it would not detect visible light, it only detected in the IR. Operating temperature, and this is a big deal right here, 35 Kelvin. We would have to keep things from freezing on the detector, because even air freezes at 35 Kelvin. We would have to pump this thing out and hold a vacuum down to like millitorr. So this thing is sealed up really, really tight, and then we cool it down. And it would take, typically to go through a cool down cycle and then warm it back up would take about a week.
It's like negative 110.
It's more than that. So take it would be negative 240 degrees Celsius. Don't ask me in Fahrenheit.
It's actually 0 again?
0 Kelvin.
Yeah. In Celsius, I mean.
In Celsius, negative 273.
Okay. Right, okay.
Yeah.
I did the math wrong.
Okay. So a lot of work went into that, a lot of precision into that. When we're doing tests, you wanted to make sure that everything was right before you sealed up the door and cooled it down. Because if you forgot to hook up the detector or something like that, or you put the filter wheel in the wrong position, it's a week before you can get back to work. A week to go ride your bike and go hiking and work on other things. Dark current, they wanted it below 400 electrons per second. What we were actually measuring was about 1/10 of an electron per second. Dark current, again, will limit the amount of time you can sit there and look at something, because eventually just the dark current will actually take away all your well. Noise was we were reading at 26 electrons, and our quantum efficiency, the percentage of light we were getting in that we were actually detecting, was up in the 90s. And it was a couple percentage points better than the Mercat Telluride, which Al would beat his chest and brag at all the conferences and make the Rickies mad. Defective pixels for a science grade device, we were measuring about 100. If they made connection, they were good. Our problem was when we squashed the diodes together with the CMOS imager, we tend to lose corners because the pressure wasn't exactly perfect between there. It was pretty good, but not all that great. So from that, what I did is I jumped over into the visible light. And these are not as good of imagers for accuracy. These are for like regular navigation cameras, for chatting with people cameras, things like that. The biggest advantage we got out of this was CMOS. We could use a standard CMOS process. There was no squashing, so they were cheaper. We could make them about $5 a piece. We were at 500 nanometers at the time. We went down from that. We had both analog and digital outputs out of this. This required a box of electronics that's sitting there between me and Paul Schmidt, guarding it carefully, that had about a dozen circuit boards in it, a preamplifier, and wiring inside the doer, and there was a couple of MOSFETs inside the doer too, that we didn't talk about. MOSFETs work wonderfully cold. So it's a whole 18-inch rack, about yay big, full of electronics to drive this thing. What we're shooting for with the VIDI was be able to drive it with a 5-wire interface right there. Most of this camera right here is the lens. The actual focal plane is just this part back here. So tiny camera. Our first version of this was a 512 by 512. We had both analog and digital outputs. So you could get analog voltages out of here, or you could read just streams of digital numbers in a screwy format that the whole world hated, except for us. The pixel was 12 microns squared. When we talk about quantum efficiency, it's down at 42%. We don't care. We're taking fast pictures. We have enough light, so losing half the photons doesn't affect us that much. Now, back in the IR days, we're measuring dark current at 0.1 electron per second. This is 300 picoamps per centimeter squared. That's a heck of a lot higher current. You wouldn't know that, though, unless you actually did the conversion. So this is one point where you have to, for the project, you have to kind of like compare apples and oranges and think about what's going on. Noise wasn't horrible, 40 electrons, but a little noisier than the Aladdin. Full well, we could collect 325,000 electrons before we saturated. Perfectly fine, because we're going at really fast shutter speeds. The shutter speed on the Aladdin is like an hour. The shutter speed on the VIDI is maybe like milliseconds. The shutter speed on the next one we're going to talk about is more like microseconds. So a lot faster. We got there was a 10-bit ADC on board. There was one for each column. And I did finally get this up. When I first got there, they had one that had like, it would give you 10 bits of data, but only 5 of them were meaningful. And so we got that up a little bit more accuracy. And the power consumption, 10 milliwatts at 30 frames per second. Think about how much power that rack of electronics generated. It was a lot more than 30 milliwatts. Nobody cared as long as it didn't heat up the dome. The power supply, okay, so you could not heat up the dome. No, not even like 1/10 of a degree. Not allowed. And so our power supply was actually located, which generated the most heat, was located 300 feet away in a separate control room, which meant we had to run 300 feet of cable through the telescope to hook it up. And I don't think our perfect power supply was perfect by the time it got there. Probably a lot of noise and pickup. And you don't know what it's like arguing with people who've been someplace since the 1950s, why you have to run a 300-foot cable through there. There's a whole like kingdom of telescope running cables. It took me a year of me being stubborn and yelling at people and throwing tantrums and all that good stuff. But we did finally get our cable. It was a miracle. and they didn't want to change anything, so they used these obsolete connectors. This is the real world here. So they're using these obsolete connectors, so they have to buy them through like these secondhand channels and everything like that. And the price of the connectors got up to be really astronomically higher. They were like $400 each. That wasn't the bad part. Each of the pins for the connector, you had to buy the pins separately. They were $300 or $400.
Oh, jeez. No, you talked about this earlier in the class.
Yeah, it's the real world. So this is what the video looked like. My piece of it is this strip right here. This was the microcontroller. This controlled all the timing and the controls and the DACs and everything like that. The actual pixel array, the part that catch light, is this region right here. This is the ADC, and you can see the various sizes of the capacitors getting smaller as it goes down there. It was 12 micrometers wide by about a centimeter for the scale here. And there were 512 of them in parallel. So when you read out a row, what you would do, you'd address the row and you'd say, I want to read it out. It would read out all 512 columns in parallel. If I was getting analog data out, it would just come off of here in an analog data stream. If I was getting digital data out, it would come out through the D outline, but it would be a string of 10-bit numbers. Had to transmit fairly quickly. I'll tell you what our protocol was, because we liked it. Our protocol was basically you got 2 bits high, meant you were starting, that there was actual data coming out. After that, we just spit data out at them. And yeah, they designed an FPGA. The Martian guys had to design an FPGA to actually interface with this, because it's like, so 2 bits are high, that means data starts. But there's a lot of times when 2 bits are high. Well, you're just going to have to wait for it. 5-wire interface, that actually got us into trouble. They wanted 4 wires. They had 4 wires in the Martian budget for this camera. They wanted to get rid of the reset line. Data in and data out was actually 1 line. This isn't quite right. Me too. There was another very important line coming into here, which was called reset.
They wanted to get rid of it.
They wanted to get rid of reset. And I'm like, are you kidding with all the bugs on this game? Don't do it.
Like, it's like the thing you have outside your office that says, one of the things like insert bug and move on.
It was the predecessor to this that they actually wanted to put on. The VIDI was fine for the Mars rovers, but the predecessor to this was the dice chip, and it had no reset. And none of the flip-flops inside the device had a reset either. That's why it didn't have reset. So basically you power it up and you had about a 20% chance that it would power up in a state where it would take a picture. And that's why
That's not great.
Yeah, that's not great. So you just have to power it up and down 10 times until you can finally take a picture. Then they named it the dice chip. You roll the dice and see if it will take a picture. You could just leave the power on once it got in there.
Reminds me of a caption project that I heard about a while ago.
Okay. So this is Me2's block diagram of this. We have the pixel array, we have serial data out, we have analog data out that actually came on, those came on the separate pens. If you wanted to, you could take parallel digital out, but not with a 5-wire interface. You have VDD and ground. There was a reset Me2 on this chip. Clock. Inside here we had a controller, and I designed the entire controller and laid it out myself. Believe it or not, I laid this out myself. I mean, if you were in the 380 lab with me, you know that my layout skills are a little bit limited, but I had this wonderful thing called an auto router.
Auto routers are really cool.
Yeah, they are, but they don't work all that great all the time. And what I did is I wrote a C program to tell it where to put the pads, which order to put the IO lines for this in, and what location they were going into. And I'd hit the auto route button, and it would usually do a fairly good job, but there would be somewhere between 2 and 50 lines that it wouldn't route. It would take about an hour to do. So I would hit the auto router and do it, and there would be like 50 lines that needed to be routed. So what I would do is I'd hit the auto route button again and let it try it the next time. The next time it would have a completely different solution. And maybe there'd only be 4 lines I'd have to route by hand. Then I'd go in and route those 4 rubber bands by hand and get something that worked. My size constraint limitations on this were I had to fit in this amount of height. And it didn't care how wide it was. So I put size constraints on it of whatever that height was, I don't remember, 2 centimeters, and the width could be infinity. So I had a really long, skinny processor. I just put it to a really high number. Nobody cared. And yeah, it was an amazing improvement over the previous version where they had no resets on the flip-flops. The state machine actually executed in an orderly fashion. The old state, it was a complete redesign. We just started from scratch because the old state machine was basically, the best way to describe it is it was a mess that was done by 2 PhDs, but one from, yeah, I won't talk about her. So, and it was like a little pinball. They had a pointer, they had these pointers in there. And the idea was as the state moved on, you move the pointer from this state to this state to this state. And sometimes the pointer would split in 2 and go in 2 different directions and then come back into a single pointer later on. And sometimes it wouldn't quite make it back and they wouldn't quite meet. And again, that was just one of the reasons it didn't work. We had one master counter that counted, one master counter. We just based it on counters. It was a good design.
Me2's design?
No, this is not Me2's design.
No, you said this is his block?
It's his block diagram. You know, he did that. Guan Yang did the pixel array. Monica, and he was from someplace in Jersey.
Somewhere.
Yeah. Monaco Ortiz was from Berkeley. He did the ADCs. Let's see who's on here. Ken McCarty, he was the guy from Mentor. He started out helping me with the design of the microcontroller, and then went to mentor. Bruce Hancock did the overall planning of the chip. I did the microcontroller. No one's too sure what Tom did, but he had a PhD from Yale, so he was okay.
He's advised.
You know what they teach people at the Ivy League schools more so than anything else. It took me a while to figure this out. It's command and control. And unfortunately, some of it rubbed off on me, but I teach now, so it doesn't really matter. How to walk into a situation and figure out how to get out of it with doing the least amount of work and the most amount of credit. But Tom was a really bright guy, and he would like negotiate contracts and do things like that, work with other groups, get us funding and money and stuff like that. Rob Sturgill was in that category too. And then Chris Wrigley and Charlie Hope are test engineers. So let's talk about the Klinefelter chip. I'm sorry, it goes into stories. I can't help it. It's CMOS images.
It's fun.
It's fun, but you don't have to do a whole lot of work on this. There's no homework. You just have to read the papers and do the projects. So this is a Klinefelter imager. It was a little bit later. The idea here, the frame rate, look at this, 10,000 frames per second. High resolution video. What would you use? It's in the visible light. 10,000 frames per second. What are you going to do with this? It's 352. Every second you get 10,000 times this many amounts of data times however many bits your ADC is. And it's an 8-bit ADC. Bits out every second. So the data rate, in order to maintain this, is 1.33 gigabits per second. Doesn't sound great now, but for the time, this was a huge data rate that you have to be able to read out. So FIFOs and pipelining and all that good stuff. What would you need to take pictures of at 10,000 frames per second? Obviously not astronomers. Well, unless it was a high energy event.
Very high energy astronomers.
Yeah. Well, no, there are people like that I can't remember his name now. The guy from Johns Hopkins that would come in, he would want to take these high energy photons, not photons, yeah, protons, the high energy particle radiation events that they would see. He wanted to take pictures of those really fast, but they weren't even at 10,000 frames per second. Let's say you wanted to watch cells dividing, and you wanted to get in a lot of detail of what was going on. You want to watch a missile going across the sky, and you want to get a lot of the detail in there and slow it down and see what's going on. So this is kind of a sciencey imager, and for something where you need a really high frame rate, it's kind of a specialty niche camera. The VIDI is more of a general purpose camera, and that Aladdin is more, it's an IR designed for low noise and long integrations, where this is the other extreme. This is really fast. There's an 8-bit ADC inside of every pixel. So let's look at the what you don't go straight. You don't do anything in the right order, Dr. Brown. We'll get to that. We'll talk about that more later. Okay, so let's go into our side here. How do we do a readout? This is the 3-transistor DRAM like we saw back in chapter 1. This is the cell, the 3-transistor configuration that made it into the VIDI, that made it into the early Hughes IR arrays, and then their astronomical arrays. I put a 4th transistor in there. Where am I storing? I'm storing right here. That's my storage node. If I want to write to it, I am going to have to pull the row strobe on high to allow current flow or charge to flow through here. And then I'm going to put the data in on this line. I have to enable the right strobe. So if the right strobe is true, this transistor goes on and I can write from here to here. If I am, what's the read strobe? Oh, that's the read strobe. If I am, no, never mind. Just forget everything I just said. I'm thinking, I'm sorry, I'm mixing up memories. If I want to write, I set right strobe high. Right strobe goes high. I turn this transistor on. It becomes transparent. Whatever's on the data line gets written directly into the capacitor. Now I want to go the other way, and I want to read. This is read strobe, not row strobe, what I said before, read. I want to read it. I turn on this transistor, which turns on the SFD, the source follower detector, and allows current, if this is voltage is high enough, well, it's a source follower. So depending upon what this VGS is will determine the current through here, which will determine how much that capacitor actually draws off of there. Okay, so I want to build this, and I'm Guanyang, and I'm amazing at squeezing 3 pounds of stuff in a 1 pound box. I look at this layout and I want to draw a cartoon of this layout. So this is the schematic as it makes sense to an engineer, circuit design engineer. I want to draw a schematic as it would make sense to a layout engineer. And if you look at this, this was going to lay out much easier than trying to figure out how to lay out this. What I've got here, I've got 2 transistors in series. So the place where I see 2 transistors in series are M2 and M3. The one that has a connection to the gate is the M3. So this must be M3. This must be the row strobe. I'm going to change colors. That's not showing up. That must be the row strobe. So this is in series with that, and its source or drain is tied to ground. This must be M2. I've got that transistor in there. The gate of M2 goes back to the drain of M1. So this is M1. And M1's gate is at right strobe. And if you look at this, this would be really easy to lay out, because what I do is I put these 2 transistors in series, and you've seen this trick before. I just put 2 gates. The drain of one is the source of the other. And you can compact it down to a very small area. This is what Guanyang did. He made our 3 transistor readout as small as he possibly could to get our fill factor up. And he was great at this. He would go, you know, he would give him a spec for fill factor and a process size, and he would just keep on making the pixels smaller and smaller. Smaller pixels have better resolution, better spatial resolution. So he kept on making the pixels smaller and smaller so we could get more detail into those things. So basically, now we're back to the Kleinfelder thingy. I've got a photodiode. Inside the pixel, I put an ADC. And I also put a memory so I can store it as I'm trying to read this thing out at gigabytes per second into my digital readout. And it's a very simple ADC. It's a ramp ADC. I have a ramp voltage, a comparator, and an 8-bit memory to store it. Not highly accurate, but extremely fast. And there's a block diagram of this thing. And pretty much what I'm doing, for some reason, they used a gray code counter. It's easier to build. I have a ramp input, and I have my signal input, and I'm comparing my signal input to the ramp. When it crosses that, I latch that value into the memory. Fairly simple. We'll look at the layout in a minute. Oh, good, we're getting there. For timing, what I want to do, and this is what I was doing, a lot of what I was doing was generating these timing diagrams. I reset the pixel. I wait. After I reset the pixel, I'm going to wait an amount of time, and then I start the ramp and I do the conversion. And this amount of time in here is called the integration time. It's the amount of time that I'm allowing light to collect. I'm allowing light to collect inside there. After I've done the conversion, and that can take up to 256 of these clock cycles. Doesn't seem so fast to me. Then I have to read it out, read out the data. And do this all in 100 microseconds to get a 10,000 frames per second. You notice the layout's a little bit different than the VIDI. Because I've got most of the readout electronics, the ADCs and the memory storage are inside the pixel, I don't need that big controller on the side. I don't need that big string of ADCs on the side. I just need, in fact, this thing isn't controlled very well at all. I just have a column mux and some drivers. I've got some power controls and bias setup over here. I've got the row controller over here, and I've got this control in the sense amps and shift register output for all that data that comes streaming out of here. The pixel layout, look at this. The fill factor is horrible. Astronomers would kill me for this. I've got the photodiode is just this little area right here. I've got an amplifier and a comparator up here. Look at all those transistors. And I've got a counter. My counter is most of this. Pretty much as you're going into the fact. Yeah, I can't see it. I got my glasses on.
That's crazy.
It is. It's a lot of stuff for every pixel. But again, this is a pixel that's capable of doing an ADC conversion, storing the value of that ADC, and spitting it out at a 1 gigabit per second rate. DRAM. If you look at these, they all have the same type of readout. It's an array of things that we need to read out. Except for DRAM and flash, we're only reading them out at digital values, unless you're trying to design a puff out of it and trying to get analog values out of it. Yeah, we're actually reading analog values out of memory. CMOS imagers, instead of having that storage node storing a 0 or 1, we're putting an array of photodiodes in there. And those photodiodes, okay. Waiting for that. Those photodiodes are going to collect light, and you have to read out an analog value there or a digitally converted analog value through an ADC. But amazingly similar architecture, which is why I wanted to teach this class to begin with. I wanted to talk, okay, and this is just inside the pixel. This is interesting. This is more about how we read them out. Typically, this is the most noisy way to do it, and this is what they were doing when I first came to JPL. I reset the whole array, and I assume every pixel gets reset to the same value. Boy, that's a miracle. I integrate, so I wait an amount of time and let light collect on this thing. And then later on, I want to integrate every pixel for the same amount of time. Timing and controller person's problem. And then I do an ADC conversion and I read that out. It's the most horrible, noisy way you can read out an imager. Now, this correlated double sampling, which is also called Fowler sampling, and that is the same Fowler.
Same Fowler?
Yeah. This is the idea here. I reset the array, and then I read I do an ADC conversion on the reset value. So I know at that temperature, at that time, at that aging rate of the array, what value was in that particular pixel. I know what value was actually reset on that pixel. And then I wait the integration time, same time on every pixel, and I do an ADC conversion on that and read that. This is called correlated double sampling. The value that I read is I just actually subtract these two numbers. And the difference between those two, and I'm frozen, and the difference between those two ADC conversions gives me my signal level. So between reset and actually read, and I'll be back in a momento. Slide